And we're trying something new this year by having academic showcase to really allow people to learn some about the exciting work that's being done at the university. And I'm just delighted that you've all chosen to join us. The topic that we chose for today is data-driven discovery. I think we're all very much aware of how data, information, and computing have really changed just about every facet of our lives. It's hard to think of any area of the economy, business, social networking, et cetera, that's not been influenced by this. And just like these advances are transforming everything from healthcare to the arts to education, it's really changing the way we think about the work that we do at a university. It's impacting just about every area of inquiry, from the humanities and the arts to the sciences to biomedicine. And it's also changing the way we think about educating and training our students. So this fall, we opened a new school of computing and information to really help us bring together all the very interesting work that's going on across the university. We're hoping that this new school is going to position the university to be a real leader in this area. But as you're going to see today, this new school is really just a piece of a very broad effort in the area of data and computing that's going on at the university. So I'm pleased to have all of you with us today, but I'm also very pleased to have this distinguished panel with us that represent just a sampling of some of the work that's being done at the university that's being driven by data, by information, and by the increasing power of computing to address some of these issues that we've been looking at for a long time. So we're going to begin by hearing from each of our panelists, and they're on a very tight timetable here because we know everybody wants to be sure to get out in time to go to the football game. So after they've each had their brief introductory remarks, I'm going to pose a few questions, but I want you to be thinking about what your questions are, because my questions are just going to be a filler till we get to the questions that you have for the panel. So first, I'm going to introduce the speakers, then I'm going to sit down and let them move along. So first to my left, the first one on your left too, I guess, is that right? Is Rebecca Jacobson. Rebecca, until very recently, was a faculty member in our Department of Biomedical Informatics. She recently, though, transitioned into the private sector to work as the Vice President for Analytics at our partner UPMC Enterprises. Her research is focused on extracting meaningful information out of electronic health records to have an impact on precision medicine, on population health, and on the quality improvements in medicine. And she's been using a lot of natural language processing methods to develop these techniques. She's going to be followed by Paul Cohen, who just joined us this fall as the founding dean of our new School of Computing and Information. He's an expert in artificial intelligence, and before he joined our university, he served as program manager at the Information Innovation Office at DARPA, which is the Defense Advanced Research Projects Agency. When he was there, he oversaw programs that addressed areas such as communication between humans and machines, cancer biology, extracting knowledge from text, and national and global security. Next is Michael Kohler Ici, also a new face at the University of Pittsburgh. He just joined our faculty this fall as the William Dietrich Chair of Political Science. So the work he does leverages this increased availability of data, information, and computing to look at digitized text and analyze patterns, excuse me, of national security, of secrecy in a democracy, international and interstate violence, and also changes in human rights over time. And finally, Jeremy Levy, who's not new face here at the university. Jeremy's a distinguished professor of physics and specializing in condensed matter physics. He's also the director of the Pittsburgh Quantum Institute. The Quantum Institute was established in 2012 to help unify and promote quantum science and engineering throughout the Pittsburgh area. He's also a very distinguished scholar. He's received the Chancellor's Distinguished Research Award twice, once as a junior faculty member and then as a senior faculty member. And he's also won the Chancellor's Distinguished Teaching Award. So we have a very exciting panel here, and I'm really looking forward to hearing your comments.
Thank you, Dr. Beeson, and welcome to everyone. Is that on? I'm not sure. I think it is. Good. Can you all hear me okay? Good. So I'd like to pick up on the theme of data-driven discovery as a transformer, and especially in biomedicine, because I think it's really fundamentally changing the science of medicine as well as the practice of medicine. And I'd actually like to start by giving you an example. It's sort of a national or a global example, but it's something that Pittsburgh and University of Pittsburgh and UPMC have been very closely involved with. And that's a project called the Cancer Genome Atlas. It has the acronym TCGA, which is very fortuitous because, of course, TCGA represents the initials of the building blocks of DNA. And this is a very large data set that has really reshaped our understanding of cancer biology as well as the practice of oncology, the practice of taking care of patients with cancer. As you all know, cancer cells are fundamentally different than normal cells. For example, cancer cells develop a myriad of different types of mutations, and these mutations drive the behavior of cancer. So what cancer is susceptible to a particular drug or resistant to that drug, whether the cancer will metastasize, et cetera. So we know that there's a huge amount of information buried in this detailed data that exists within these rapidly changing cancer cells. But really, until this project began, it was very difficult to understand that because we were going after it in a kind of hypothesis-driven, one experiment at a time kind of way. This project was quite novel. It was a project of the National Institute of Health, National Cancer Institute, but it was one that we, as University of Pittsburgh and patients from UPMC, were one of the major contributors to this project in terms of the samples that were used. The project included the medical history and tumor samples that were collected from 20 different institutions, including ours, and from 11,000 patients who had a total of something like 33 different types of cancer. And what happened was that from these samples, the entire genetic code of the cancers were sequenced across all 11,000 patients, and a lot of other types of molecular information was included, and it created a database that was 2.5 petabytes of data. To give you a sense of what that is, that's like roughly a quarter million DVDs of data, okay? And the great thing about this project is that over the decades since it started, it has created a cascade of information about cancer, about the biology of cancer that has changed, for instance, our ability to detect and subdivide cancers, and also it has created the opportunity for new therapeutic methods because we understand this biology so much better. So what's driving this kind of increased use of data-driven discovery in biomedicine? And I really think it's a number of different factors. The example that I just gave you, the one of the Cancer Genome Atlas, part of what drove that was the fact that we have rapidly changed our ability to sequence and collect molecular information. It is much, much faster and much cheaper and much better than it has ever been. And in part, that derives from great engineering advances that made that possible. So for instance, you all may remember a project called the Human Genome Project. It started previous century, I can say now, and was really kind of concluded largely by 2001, 2002, 2003. And that project sequenced the first human genome. It cost took about 15 years. It cost about $100 million. Currently, we can do the same thing in approximately an hour and at a cost of about $1,000. So because of that, the ability that we have to generate this kind of data in biomedicine has really rapidly advanced, and we're generating data at an incredibly rapid rate. And that's both scientific data, data where people are kind of looking at things specifically for scientific research, as well as clinical data, as patients for a variety of different conditions have sequencing that's performed. So that's one thing. I think another major advance that's driving this is electronic health records. So now we have the ability to collect much better data from patients, and that tells us something about kind of the outcomes that we need to understand what happens, so that we can sort of look backwards and see what are the driving features that are associated. A third factor are better, faster, and greater variety of algorithms, and I think we'll hear about some very exciting things from the panel. I can tell you that at DBMI, for example, a new center that's been there for a couple of years now, which looks at how do we define causal? How do we define what is causal in data? Because that is a real problem in these kinds of very large data sets. A fourth factor, faster computers, cloud computing, and better infrastructure that make this feasible. And then finally, I think there's a growing recognition, including at NIH, that the methods that we used, for example, like clinical trials, which are very expensive and costly, while they are very important and not necessarily to be done away with, they can be augmented by these kind of data-driven methods. And so that's an important change as well. So the potential of these data-driving approaches is very exciting, and I want to give you a couple of examples of things that are going on here. The first one is in the kind of area of diagnostics. So I mentioned that the genetic code carries a lot of information, and one of the things that it carries, the kind of information that it carries, is whether how you respond to drugs. And so, for example, there are people whose genetic code makes them more or less able to metabolize specific drugs. And as an example of where we're really bringing that into practice, I'd like to note the work of Dr. Phil Empey in the School of Pharmacy, who has been working with UPMC to use this information so that they can predict who will or won't respond to the drug clopidogrel, which is used for patients who have cardiac catheterization, for example, to diagnose and to treat blockages of the heart arteries. And so what Dr. Empey is doing is so unique because it actually brings this information into practice. The second example I want to give you is in the area of radiology and artificial intelligence. And this is one where currently most radiology images are examined and diagnosed by radiologists, obviously, but there's been a huge advance in the algorithms for image analysis. And so we're starting to see artificial intelligence and image analysis merging together to really change the practice of radiology. And the example that I want to give you here is one that's being done at UPMC Enterprises by colleagues Dr. Chris Dybel and Brian Kolowitz, and that one is really focused on identifying patients who have a specific abnormality, something called a pneumothorax. It's air that collects between the chest wall and the lung, and it can be life-threatening. And the idea is to use this image analysis to very rapidly, as soon as the thing comes off the machine, detect who these patients are so that we can treat them. So in summary, I think the potential for these methods is enormous. We're starting to see them come into medical practice, and I'm really looking forward to hearing what the other panelists have to say as we go down this road towards data-driven discovery in biomedicine. Thank you.
Thanks, Rebecca. So I'd like to pick up on a comment Rebecca made about causality and the relationship between correlations or associations and causes. And you've all heard this before, correlation is not cause. Data-driven discovery today is largely about association or correlation, not about causation. It's really important to understand that. You find an association between a person's genome and some aspect of their physiology or their behavior or some disease. You find an association, it's a statistical association. That doesn't mean you understand how you got from the genetic code to the way the genetics manifests, the phenotype. data analytics can tell you that a drug affects a disease, but you often won't understand why the drug works. And this lack of mechanistic understanding shouldn't bother you. It's not a bad thing if you can reliably achieve your goals, controlling disease, by exploiting these correlations. But there are other times when you really need to want to know what the underlying mechanism is. If you want to improve upon a drug, for example, or if you want to know why it works in some people but not others, something that Rebecca alluded to. Or if you have a lawsuit going on that demands an explanation. In all of these cases, you need to know what the underlying mechanism is. When I was at DARPA, as Patty alluded to a few moments ago, we started a program called Big Mechanism. And Big Mechanism is a poke in the eye. The name is a poke in the eye to big data. We wanted to see whether we could develop technology not only to discover correlations or associations in data, but to discover mechanisms in data, discover the causal relations in data. And more specifically, we wanted to develop technology to find the molecular causes of cancer. Now, there are two main approaches to finding causality in data. The first, that Rebecca alluded to, is essentially statistical. You define causality in statistical terms, and then you develop algorithms that will find things that have the statistical signature of causality. People will tell you that you can't get causality from correlation, but that's actually not true. You can. It's extremely hard work, and the algorithms are complicated and they run slowly, but it can be done. In fact, Pitt and CMU are two of the best places in the world for that kind of research, and here we have a joint institute called the Center for Causal Discovery that's all about trying to find causality in data. There is another approach, though, and it's the one that we took in the Big Mechanism program. It's to read the journal articles in which people make causal assertions. Just read and see what people say, what causes what. This takes a highly trained human between an hour and a day per journal article. It takes the machines that we developed in Big Mechanism about 5 seconds per paper. So we can read hundreds of thousands of papers. So one paper might say that protein A binds to protein B, and together they do something to protein C. Another paper might say that drug X reduces the amount of protein A, and so on. And you can start to imagine how you build up a causal story. And these sequences of causal assertions, these this protein does something to this protein, that does something to this protein, these things are commonly called pathways. And there's a great industry now in trying to figure out what are the molecular pathways that cause cells to behave in the ways they do. Some mutated proteins have either create new pathways or have bad effects on pathways, and that's what results in cancer. Now you can imagine that if you can read a paper every 5 seconds and extract from every paper a little piece of a causal pathway, and you can glue all those causal fragments together to get these big, long pathways, you should be able to get mechanistic models of cancer, and indeed that's what you do. You can think of cancer pathways, if you like, as a roadmap, sort of. Do you remember back before Google Maps, right? You would actually open an atlas and you'd see all of these roads. Well, imagine each town as a reaction between, an interaction between proteins, or interaction between drugs and proteins. Each town is sort of the result of the things that feed into it. And you can think of drugs, if you like, as proteins that are blocking the roads on those pathways. So if you had such a roadmap, your job would be to place roadblocks, that is drugs, between mutated proteins and downstream mechanisms that you really want to control. Ideally, what you want to do is you want to make the cell stop dividing and die, right? But you do that by placing these roadblocks in the way. The other thing, of course, is that if you had such a pathway, you would just quickly discover that yours isn't quite the same as mine. You would see that the roadmap, your roadmap is slightly different than my roadmap, and that's the sort of entry into precision medicine, because I want to be able to place roadblocks that are just right for your roadmap, not necessarily for mine. And indeed, this is what we were able to do in the Big Mechanism program. We were able to read last count, 300,000 papers, and build these enormous roadmaps and figure out where to place roadblocks, that is, where to drug these pathways in order to control tumors. So I want to summarize this story with what I think are 5 germane lessons for data-driven discovery. First, we have to expand our notion of data. I think most people think of data as the kind of thing you see in Excel spreadsheets, just tables of numbers. I think journal articles are data. We have to expand what we mean by data discovery algorithms. Most people think that they're statistical algorithms that work on numbers. I think that machine reading is a data-driven discovery algorithm, right? Machines that can actually read the literature are discovering things. Second, analytics today, as I've said, is mostly about correlation and and what works, but not why things work. And we've got to put a lot of effort, as Rebecca said, into AI technologies and statistical mechanisms for figuring out the why. Third, we will see for decades to come marvelous things coming out of the analysis of associations and correlations in these enormous data sets. And those are great results, and they will save people's lives. Right? But if you want to design a therapy rather than stumbling on a therapy, then you should figure out what the underlying process is that you're trying to control. Right? And that's the causal aspect of it. Fourth, people talk about big data as if it's a solved problem. Certainly the companies that are snapping up our students think it's a solved problem, but as these examples, Rebecca's and the one I've given you, should tell you, we're at the very beginning of the big data revolution. Right? There's still an enormous amount of work to be done, particularly in the causal world. And then finally, the general problem of discovering complicated mechanisms that run the world, whether they're cancer mechanisms or climate mechanisms or engineered mechanisms, socioeconomic mechanisms. The business of discovering those mechanisms that run the world is the real grand challenge for our century, particularly because many of those systems are under stress now. Not by coincidence, that's also one of the primary research focuses for the new School of Computing and Information. Thank you.
So I'm really, really excited to be here. Part of my job in 6 to 8 minutes is to convince you that a social scientist belongs at this table with people curing cancer, working on AI, doing quantum computing. I told my kids who I was on the panel with, and they were like, "Really, Dad?" So maybe I don't belong here because they're amazing, but a social scientist does belong here. Right? We are living through these 2 absolutely amazing revolutions, the computing revolution, right, and the digital revolution. And these digital cookie crumbs that people are crunching numbers with, right, are left by people. Right? We have an amazing panoply of high-resolution data on human decisions at the scale that people are making it. Streaming data that people are typing into a computer and we're capturing it. Paths and decisions of where they're going, and these are created by people. Right? And so their decision-making, I think, is absolutely critical to understanding the mechanisms that's going on, the delivery of medicine, right? Understanding and unraveling the meaning of text and how they wrote it, right? And truly, that's what I want. My career is sort of based on trying to bring these ideas of machine learning and AI and point them towards these, what you can think about as huge lasers, right, that people are building, and point them to social science questions like inequality, human rights, violence, polarization, and then the insights we gain from understanding better in data-driven discoveries, understanding how people interact with each other. I do believe that also changes the models and tools and the lasers, right, that we're building, right, to better understand the world. So my work is sort of in this area called computational social science that really sits at the interstices of computer science and some engineering perspectives and sort of the more quantitative social sciences like economics and political science. Some of the things I work on that I'm really excited about, maybe I can make other people excited about too, right, is basically understanding human rights. So as an example of data-driven discovery in the social sciences, for about 20 years, if we wanted to know which countries were violating human rights, were oppressing or not, what we did is we'd have NGOs and governments write reports in text, and we had poor undergraduate and graduate students, yes, like you or your like kids, right, just reading these things and then assigning a score, right? So you went from this rich textual description of the events that would happen, and literally you just gave it like a 4, right? Which is fine because like, that was the scale. We were thinking in Excel spreadsheets. And then after you did this for a while, like 20 years of this and like a lot of money, right, spent on this, like, you know what the discovery was? Human rights are getting a little bit worse. But you looked around and it's like, that didn't seem like right. Like there's NGOs around the world now and we're trying to crack down on landmines and like, man, the world was a pretty rough place like, in the 1800s. Like really? Are things really getting worse? And so one of the things we looked at was, well, that's what the data says, right? At least the data as it was collected. But maybe that's not quite right. So one of our first projects, entrepose into this, was learning the mapping from the text to these scores, right? So training computers to basically replicate these 20 years of human coding, right? So we could learn a perfectly reliable mapping. And then we were able to show, because a computer can do this, right? Like you give it the same text, it will always give you the same answer back, right? It's replicable in that way, right? And then we can fit it across time. And what we found out is that there's huge amount of variation in the scores humans were giving, right, these texts over time. But it wasn't in what you thought. Like one of the theories that sort of came out of this data-driven discovery was that things have just gotten harder, right? Like, you know what, we're just tougher now. So we assign these really bad 5 scores, right, to North Korea, but it used to be like a 3, right, in what they did. But that's not what you see. You don't just see the word like, widespread, right, getting a 3 instead of a 5. Instead, there's all sorts of nouns, right, that appear that were never used before. The vocabulary of human rights has shifted, right, over time. And in our second project, we went to the text and built models of, like, well, how do people compose these texts, right? When you think about, like, what is the data of the world and how do they sit down and write? So we wrote models of these things. And really, we were totally inspired by work in computer science on movie reviews, right? So you can think about human rights reports as, like, a movie review, right? Like, the movie adaptation, like, I liked, right? Like, but I don't really like Nicolas Cage, right? But I like the screenplay. And the human rights is the same way, it's plural, right? You can like or dislike different things about human rights. So North Korea gets an overall splat, right, on just about every aspect of human rights. Norway gets like a fresh tomato, right? Like, they do great. But then there's other countries, including the US, that get mixed ratings, right? There's certain things, right, that countries do well and other ones they don't. And so what we can do is use tools to extract these aspects and the judgments being offered on them and then track them over time. And we were able to show that the definition of human rights, what's being judged has changed, not how they were judged, right? That human rights is more plural today than it used to be. And then we found this amazing sort of conceptual map about how they're organized, right? It's not that there's just more, that what we've done is we've zoomed in on the concept of human rights, that there was this thing called physical integrity rights, but now we have sort of judicial killing and extrajudicial killing. There's radial types of torture, right, that are discussed. And I think for me, what this brought home is that the sort of operational analogy, I think, for big data in the social world, and I think it's across many of these things, is that what we have is multi-scale data, right? And text is like the greatest example of this, but maybe the easiest example to understand is Google Maps, right? All data is like a Google map. Like, and we do this, like, one of the reasons we love interacting with Google Maps is because we pinch to zoom in our heads, like, all the time, right? We're always thinking at different scales of conceptual meaning, like, back and forth. And like, so text is like this too, right? We can put piles of documents and separate them and classify them, but then we can go read, right? Individual sentences and see whether our inferences really fit what was there, right? And this is important because what we can do is we can have theories at one level, right? Like human rights over a whole country, right? And human rights overall, but we can use data to unpack that and understand and drive new theories about how the world has changed, right? And so we're doing this across Civil War also. So one of the things that we've talked about is, so political violence is something that I'm like passionate and interested about. And we used to just say like, well, can we just forecast, if there's a civil war in a country at any time in a given year, right? But with new data, like satellite data, point processes, being able to track like exactly what's happening, like we have projects now where what we're trying to do is actually forecast violence within a 50 kilometer grid cell, right, for all of Africa. right? Like we're zooming in. That doesn't mean that the sort of larger country level things like government instability are unimportant. It just means we have to be able to track, to have mechanisms that go across these scales. We can't do it without like friends in computer science and collaborators. You know, one of the things that's really, really important for doing this is that we need both domain expertise, right, for the mechanisms and all this, but we need engineering expertise because, like, while I love to code and I teach social scientists how to code and sort of how to ride these waves of the computational and digital revolutions, right, I need help doing it efficiently. And so I think one of the things that excites me about Pitt is just how it's building institutions for this interdisciplinary, the bringing domain knowledge at different scales so we can learn, right, from each other's skills and basically learn things and expand human knowledge in ways we couldn't do without each other. So I'll stop there.
Wow, I've been amazed to hear. I'm here. I have a front row seat listening to all of this amazing discussion. I hope we've not reached cognitive overload yet. So I'd like to talk about basically two quantum revolutions that are defining both my field and actually in information and what we mean by information. So my background, I'm a physicist, and so I think in those terms. But if you look back in the 20th century and we think about all of the technology that has emerged, right? Computers, lasers, all the information that basically now fits in your pocket. All of this really stemmed from our understanding that the world is quantum mechanical. So I'm not going to now, launch into a discussion of quantum mechanics, except to say that in 1925, Erwin Schrödinger wrote down a single equation, the Schrödinger equation, and that single equation, for example, completely redefined and provided a foundation for the entire field of chemistry. It provided an understanding of materials that allowed us to make computers, basically to understand why some materials conduct electricity and others do not. And that's, of course, really important because the electrical flow plays an essential role in the storing and processing of information. So our understanding of information is really strongly coupled with our understanding of the world and the universe, right? So actually the laws of quantum mechanics, we believe, permeate not only our cell phones, but they go out into the deepest reaches of the universe. We believe that the entire world and universe is quantum mechanical. And so really over the course of this last century, right, this is really what we call the first quantum revolution, where as we begin to understand more and more about how materials work, understanding their properties allowed us to exploit those properties. So all of the information that we store now is a consequence of what we understand about these materials. And so this is, of course, has been incredibly important in a number of fields, and all of the data that we're storing, as I said, comes from that. But as you know, we're sort of reaching the end of Moore's law, right? You may have heard how Moore's law is over or is almost over, and then you hear, oh no, it's not over. We have another 5 years. Well, that was like 5 years ago, right? So the fact is that computer speeds are not getting faster. It used to be that Intel would say, oh look, we have the fastest CPU on the market, and you don't see the CPUs getting any faster because basically these materials would just melt, right? And we know that, of course, that ultimately there is an end because we're not going to make the smallest units of memory densely packed at the spacing between atoms. That's just, it's going to stop before then. And so the question is, well, what does that mean? Well, are current computers powerful enough? And the answer is no, right? They are nowhere close to being able to solve the problems that are in front of us. And I think this is something that it's sort of, in some sense, a bit discussed by my colleagues here. But basically, we just now conceive of harder problems, right? So we are already at the limits of what ordinary computers can do for us. And so the question is, well, do we give up, or do we, what do we do? So it turns out that there's a second quantum revolution that is taking place, and it's likely to take maybe another century to play out. And it's really a shift from, it also involves quantum physics, but basically the shift is that before we were simply using quantum mechanics to understand how to make materials that did not really have a fundamentally quantum behavior. But now we're able to control materials at the fundamental level of quantum mechanics. We're able to use the strangest properties of quantum physics to do calculations. As it turns out, this Schrödinger equation that I was mentioning before is a really difficult equation to solve. In fact, the Nobel Committee gives out prizes to people who simply come up with a better way of approximating the solutions to that equation, right? So there was a Nobel Prize given in chemistry for Walter Cohen and John Popel for this thing called density functional theory, which is really important for, in understanding materials, but it was just an approximation. So now we're at the point where we actually can control matter at its fundamental level, at single electrons, the spin of single electrons, and ions, and so forth. And this quantum mechanical behavior is solving the equation of quantum mechanics in real time. And those solutions can be mapped onto hard problems. So it turned out that there was a computer scientist, Peter Shor, who was working at Bell Laboratories in the 90s, basically came up with an algorithm for factoring large numbers into prime. So you might think, well, who cares, right? But it turns out that you probably should care because if you had a quantum computer, it could factor numbers exponentially faster than ordinary computers. And we rely on the difficulty of factoring numbers in all of our secure transactions. So every time you make a credit card payment, you're communicating with somebody you've not communicated with before. And so you need to share a key that can be used to encode information, and that person, on the other side, they can decode it. So this protocol is basically using the difficulty of factoring numbers and the relative ease in multiplying numbers. And a quantum computer can efficiently can efficiently crack, essentially can defeat the entire security of the internet. But fortunately, we don't have a quantum, or maybe unfortunately, we don't have a quantum computer yet. To me, personally, actually, that's one of the least interesting things about a quantum computer. What's more interesting is the fact that it can solve the most important equation in the universe, right? So that should be, right? That's important. And in fact, so understanding and predicting the properties of matter at its very fundamental constituent levels, this is really the challenge. And this is what researchers all over the world, IBM, Intel, Google, Microsoft, are pouring in hundreds of millions of dollars, increasing amounts, to attack these problems and to develop so-called quantum supremacy. So I'm really happy that here at the University of Pittsburgh, Pitt has actually been out in front in helping to support quantum research that is really at the intersection of the first quantum revolution that involves traditional departments and the second quantum revolution that really has in front of us this grand challenge of trying to build a quantum computer and to hopefully use it for the betterment of society, not just reading your email.
Well, thank you, everybody. That was, I think, just a very interesting overview of the sort of work that can be done at the University of Pittsburgh and elsewhere using quantum, but also data information and computing. I'm just going to ask a couple of questions, and again, I hope that this has generated a lot of questions on your part. But Michael, when you were talking, you referred to the need to bring in the domain expertise along with the computing expertise and the data. That's something we've talked a lot about around the university. I know Paul's been very engaged in it. So I was wondering if you all could talk a little bit about how does this impact how we train students and how we educate them in this new world where a lot of what we can do depends on being able to bring together that domain expertise with the data and computing.
So in my previous job, I built something called the Social Science Data Analytic Initiative, which was basically bringing students that were passionate about social science, but teaching them the language that like machine learning people and engineers like would use, so they could be on teams. And basically, like the class was very much a team-based class. So I think there's sort of three really, really big changes that are related to this. Like one is people have to be able to work with other people, right, of very different domains. We have to teach students how to do it better than we do in the university, right? And so we do really, really well generally, but you usually have to get over those translational things. Like we're so specialized in what we do, we have to translate into what, and so there's a funny story about when you're meeting with someone from a distant domain, you often have to get over the part where you think they're an idiot, let them get over the part where they think you're an idiot, and then you're good, right? And then you can have a conversation. So I think we have to teach students the language to get over that more quickly. And third, we have to make students that aren't necessarily comfortable with number theory and math comfortable with computers, or at least know what other people in other domains can do, right? So they can share a common goal and see the value in what their collaborative work could do. And so I think there are many, many ways to do that, but it is changing the class structure to some extent, bringing more tools and skills to social sciences is one way to do that.
Mm-hmm. Paul, did you want to comment on what you're thinking about in this area?
Sure. Yeah, I think we should completely redesign the university and teach students in a very different way. And I will say that Provost Beeson and I have talked about this, and she is extremely supportive, which is very good. So what do I mean by that? I'm intrigued by one failure and one success. The failure is what I would call the two expert model of interdisciplinarity. And this is the model that sort of prevails. You get interdisciplinary work by getting a chemist and a physicist together, or a natural language researcher and a cancer researcher together. And sometimes it works. Most often times it doesn't. It's partly the two idiot problem, if you like, right? That's the two expert problem, and it's the prevailing notion of how to get interdisciplinary work done. Here's another notion, and it was the prevailing view before Sputnik. You know stuff that makes it possible for you to work in more than one field. We used to call that liberal arts, right? Then Sputnik came along, specialization happened. It became impossible for people to understand each other. But more than that, we lost sight of the idea that there's a body of knowledge that would let you work in multiple fields. We lost sight of that idea. Ironically, many of the ideas that make it possible to work in multiple fields are associated these days with computing. And I'll give you a simple example. How many kinds of network can you think about? I talked about the road networks just a moment ago. Chemical networks, protein networks, social networks, others, energy network, transportation network, supply chains. All of these kinds of networks. And they're all taught in completely different ways. We have many courses here at Pitt about kinds of networks. We don't have a single course called networks. We don't have a single course that teaches this fundamental idea that if you get that idea, you can work in any of these other disciplines. This is liberal arts for the information ages, liberal arts for the 21st century. And it's really important that we start to develop pedagogy that emphasizes what fields have in common, not what makes them different. And I mean it. Provost Beeson has been very helpful with this. Dean Blee here has been very helpful with this. We're putting together blended majors now that blend computing with other disciplines that are built around this idea of learning the stuff that multiple disciplines have in common. And I'm very grateful to be here at an institution with colleagues like Dean Blee and Provost Beeson, because we're going to get that done.
I think sort of related, and Rebecca and Jeremy, you both touched on this, it's that this isn't contained within a university. you know, that there's a lot of connections with IBM, with Amazon, with UPMC, with the, how do we take what we know and really interface much more effectively with industry partners and others so that we can translate our expertise into really practical application that helps move the economy, society forward, healthcare, et cetera.
So I think it's a really great question, and I think that this sort of last piece between the data-driven discovery and making it practically useful is its own whole science in some ways. And I can tell you that here, just as an example of what's going on here, you know, is the Pittsburgh Health Data Alliance, which is an alliance between UPMC and Carnegie Mellon and the University of Pittsburgh. And the idea here is to take these data-driven discoveries that are going on and the methodologies that are going on at both universities to provide kind of basic sort of seed funding to nurture them and to translate them into, in this particular case, healthcare. But I think you could say the same thing for lots of other things as well. So I think this is fundamentally important, and I think we do have such an opportunity in this city and among our institutions to get into this in a much deeper way.
Yeah, so I think this is a really important question to decide how do you draw the circle of where you try to improve the communication, engagement, and collaboration, because well at universities we have departments, and departments have sub groups, and then you have this individual investigators, and so at the Pittsburgh Quantum Institute, that was one of the very early questions that we sort of not wrestled with, but we thought deeply about this, and we realized that it wasn't going to be a Pitt, either a Pitt-only thing or even a physics-only thing. So we realized that we have, not just in physics, but in chemistry and engineering, we have basically the first and second quantum revolution are sort of overlapping right now. And so we need to engage people who, let's say in chemistry, are using these approximations to the solutions of the Schrodinger equation and would love to have a quantum computer. Or maybe they're actually addressing problems which are aligned with what maybe people in physics or chemistry are doing. So basically drawing that circle is really important, but also engaging CMU and realizing that we have colleagues there in physics and material science and electrical engineering, and in some sense trying to provide an intellectual home is one of the things, the most important and core functions of a university, I think, and I guess I would also echo that I really am grateful for the support that we get in this endeavor, in moving across all of these boundaries.
And I'll just note, we even have philosophers that are affiliated with the Pittsburgh Quantum Institute. So this is really, quite broad and interdisciplinary, the work that's happening in all these areas. One of the things I find most exciting about what we're doing at Pitt is that this new push that we have is really helping us change the way we think about the work that we do. It's really breaking the boundaries, as Jeremy was saying, between departments. It's really helping us get out of our silos, and as Paul was saying, really think about education not as economics and computing, but economics computing. Bringing them together, really integrating things. And it's a challenge for us as an institution, but it is so exciting to think about the difference we can make and the way we can really change the world through the things that we're doing here at Pitt. So with that, I'm going to just open it up to questions here. We have a lot of time, and so don't be shy. Thank you.
For me, this is for you, researcher in quantum mechanics. So for the idea of solving the Schrodinger's equation and the idea that it's the most fundamental, most important question, would you think it's possible that there isn't a solution to the Schrodinger's equation, because it states that there is a state what's the state of it talks about superposition, the state, if it's a wave, a particle's wave, or if it's a particle, and isn't it possible that there is no solution to it, and that would just reveal that our world isn't exactly as like concrete as we think it is? Or do you think that all quantum mechanics believe that there is?
No, it's a very
That's revolutionary.
actually it's a very good question. The question of what can we compute, right? So okay. So now I'll tell you a little bit about quantum physics. So basically, if we think about a bit, right? Bit is the most fundamental unit of information. It's a light switch. It's on. It's off, right? It's 1. It's 0, and there's no other sort of intermediate state. So it turns out in quantum physics, well, even in an ordinary bit, a bit is actually made up of something, right? It could be a magnetic orientation of a moment or the presence or absence of charge. The point is that there's some sort of physical state that is representing this. But ultimately, everything is quantum mechanical. And one of the weird things about quantum mechanics is that if you can be in one state or the other state, you can actually be in a quantum superposition of those two states, which is a really, really weird concept. But basically, we have the 1 and we have the 0, and they're well defined in ordinary information. But you can also have superpositions of 1 and 0, which turns out to be fundamental to quantum mechanics, but also really fundamental to building a quantum computer. So I would say that we can, like solving the equations for the simplest system of 2 levels, where there's 1 and a 0, we can do that. I can do that on my phone, on a laptop. But now you can say, well, what if I want 2 quantum bits? Well, now each one of them can be in the 0 or 1 state, so there are 4 possible states. And each one of them has a sort of amplitude that you need a number to represent. Now when you go to 3, you have 2 times 2 times 2, you have 8, right? So the point is that once you get to like 300 quantum bits, you require more regular bits to simply describe 300 quantum bits, then more bits than we have atoms in the universe, right? So we cannot simulate, so in some sense you're right, we cannot simulate the equations of quantum mechanics on an ordinary computer. You need something that is quantum mechanical, or you need to make some approximations or so forth. So it turns out that, yeah, if you can sort of hijack the properties of a quantum system, then it's solving its own equation in real time. So if you can somehow control and harness that, that's really what you want to do with a quantum computer.
Questions?
So everyone's talking about the sort of revolutionary aspect of this sort of data-driven discovery. And I'm curious to get you all to predict the future. So what is it, what's an area, a discipline or an area of everyday life that you think is going to be, in the next 5 or 10 years, altered significantly, and maybe in somewhat unpredictable ways, by this, by our ability to collect, analyze, manipulate data?
I think one of the big challenges that if we could crack it would alter things significantly is the ability to bring different kinds of data at different scales about different things into one space. Most of the work that's done with big data is about a very specific problem. Right? What you'd like to be able to do, and Michael alluded to this, there are problems out there like hunger or the rights of citizens in a country that sit at the intersection of many different things. How much they have to eat, how's the transportation system, what is the mode of government, is there, what are the, how much wealth does the country have? There are problems like hunger or civil rights that we're not even going to be able to get our heads around until we can bring together data from many, many different sources at many different spatial and temporal scales. We haven't been able to do that so far. I mean, the workshop that you were running yesterday had one speaker on multimodal, essentially data analysis. It's really in its infancy, but you can start to imagine what kinds of questions we could answer if we could harness data from many, many different sources.
Oh, I should answer that?
Everybody can take a shot at what they think is the biggest opportunity we see on the horizon here.
Yeah, so I noticed you said in like the 5 to 10 year time frame. So all of the stuff I've been talking about, all the promise of cracking codes and stuff, that's not going to happen anytime soon. Maybe that's fortunately. I think one though the idea of exploiting quantum mechanics for the purposes of information security is something that has more near-term applications. So there is this field of quantum cryptography. So I was saying how basically if Alice and Bob want to talk to each other and they're worried about Eve, the eavesdropper, this is sort of the standard names given in cryptography, then basically there's no way for them to really talk securely if they're only using public channels. But it turns out that you can use quantum mechanics to distribute a key that only they share. So they're not actually communicating yet, but they're actually sharing a sequence of ones and zeros that they can use to encode and decode their information. And this is actually something that there's actually a company that makes these, and they basically send single photons over optical fiber, and I think like in Switzerland you can do it. The problem is that actually you can't go more than 20 kilometers before that photon gets scattered and it doesn't work anymore. So you need to do something called quantum error correction, which is a really weird thing. But the point is that there sort of are smaller applications that are near-term applications that do exist. Another example is actually my colleague, Michael Hattridge, who's an assistant professor. He's actually a consultant on a company, a startup company, and they make these amplifiers that are basically at the sensitivity limit that is governed by quantum mechanics. And they played a really important role in one specific approach to building a quantum computer. So there actually are a number of these startup companies that are forming and are basically trying to carve out a space for near-term applications, and they're thinking very hard about what problems they can solve. So Google has this notion of quantum supremacy, which is just a brilliant marketing term, right? I mean, doesn't it sound like every like sort of spy novel, right? But the idea of quantum supremacy is basically to identify a problem, any problem that a quantum hardware can do better than classical hardware, and they think that they're a year away from reaching that point. Now, the problem itself is not, nobody cares about that problem, but it's really more of a milestone and an internal marketing approach. But the idea is it's important to think about near-term things and not just what'll happen 100 years from now or whatever, 75 years from now when you have a quantum computer.
So it's a hard one in medicine, I think, because of the reasons we were discussing earlier, that it just takes a very long time and a lot of different effort to see these kinds of advances because of the complexity of the environment, the regulatory environment, et cetera, et cetera. But I'll give you two examples where I think in the next 5 to 10 years there'll be a hopefully significant change. One is the area that I mentioned, which is sort of the precision medicine of drug prescription. I think that will change relatively earlier than some of the things I could think about. So I think we will be in a world in 10 years where when you're prescribed a drug, it is dosed to you, or it is prescribed specifically for you because of what we know about you. And I think that's an important potential advance. The other place that I think there's a potential for making really rapid change actually relates to some of the things that Michael was talking about, which is, access to healthcare in some ways. Where do we deliver? We are in an environment with restricted dollars that are focused, our ability to focus healthcare, and we're probably not spending them the right way. We're not intervening with the right people, et cetera. So to be able to predict where things are going to happen, where the opioid crisis is going to be worst, how do we deliver our healthcare dollars in a way that is much more finely tuned to what is going to happen in the next sort of period of time? I think that's a place where we could see really important changes.
Great question. Boy, put on the spot. I'll go with 2 to hedge a little. So one is, maybe 10 years, but maybe longer. But I think what you'll end up seeing, not on the nightly news, but there will be like conflict or violence weather maps that you'll have access to if you're traveling, that you'll be able to zoom in and zoom out and see at relatively precise locations what the risk set is, for different highly precise types of violence and spatially, right, at relatively high resolution. We're building to that, and I think 10 years is a pretty good time to possibly get there. The second, which is kind of, I think, maybe more exciting and maybe more important, is I think we all think public opinion and being able to measure public opinion is incredibly important in a democracy. But people are stopping answering their phones. There's lots of problems with this, and so there's lots of really exciting research on measuring human sentiment and opinions based on unstructured data and other sources. So I imagine, I think in 5 to 10 years, what we'll see are, political and social forecasts of values and judgments that are informed by things like social media and text, outperforming public opinion as polls, in that time frame. It's a really, really important thing that, there's one of our sensors of democracy is dying, right? It's not working as well as it used to, and we need to put up a new sensor. I think it's incredibly important for our democracy, and we're starting to do that. So those are my 2. Maybe the third is that we're going to see the appification of research, right? That we're going to move from, less about paper and more about pixels. And there's, I think, great communicative potential in that also.
Here?
These 2 years, I hear a new term, cognitive computing. How do you professors think about this new technology? IBM mentioned it, KPMG and Deloitte, they also mentioned this terminology. I am interested in it.
So the term has been used to mean a bunch of things. I think you're probably talking about computers that try in some ways to emulate neural hardware.
Yeah, that is the definition from
Yeah.
Some Wikipedia or something.
Yeah, I mean, the argument is that we do an awful lot with 4 pounds of 4-pound brains, right? Do an awful lot of work using not that much energy. And so wouldn't it be nice if you could build computers that also weighed only 4 pounds and could do what we could do with not a whole lot of energy? So people are working on that. And I think from a sort of a hardware perspective and maybe a machine architecture perspective, those are really interesting projects. I think that there are some really very thorny problems. They've been with us since the earliest days of artificial intelligence that aren't going away, and I don't personally see how the new hardware architectures will make them go away. Some of those problems have to do with just the sheer amount that a human learns in a very, very short time, and sort of the commonality of what we learn. So if I were to ask anybody in this room, you're in this room, where is your nose? Pretty much everyone would say, well, it's on my face, or it's in this room. I mean, nobody would say, well, I don't know where my nose is, right? We have this amazing sort of common knowledge. Humans build up this incredible common knowledge over a period of sort of 2, 3, 4 years. It's one of the thorniest, most important problems in AI. Those problems aren't going to go away just because we have new hardware. We have to be thinking hard about how it is that the brain is built for acquiring that kind of knowledge. Another really thorny problem that the hardware, I don't think itself will make go away, is the problem of meaning. The sense you have that words mean something, that images mean something, that events mean something. This ability to extract content or meaning from physical forms, words or sound patterns, it remains a deeply challenging problem for AI and philosophy and cognitive science generally. Again, I'm not sure that the hardware itself is going to help with that. A couple of examples of cognitive problems that we have yet to solve in AI or computer science.
That's great. Thanks for your answer.
Well, I'm going to ask another question. So a lot of what we talk about in this area, all these data that are available about me, and through the social as well as the biomedical, that raises a lot of concerns on people's parts that data are out there available to everyone. So that's one piece, but there's also the way in which the data and information has to translate through people into action. So there's this real social aspect, and people are in the middle of it. Do you see some particular challenges there? I'm thinking in the biomedical area, but also in what you were talking about, Michael, and how do we overcome those sort of challenges, or are those things that we're going to be struggling with for a long time?
Go ahead.
So yeah, I think there's so much to unwrap there. Let me just take a couple of stabs at it. I think we're constantly trying to balance, right, the privacy and openness of data. And it's very challenging, and it's very challenging in biomedicine particularly because there's a lot of harm, frankly, that can be done when data ends up in the wrong place. And so there is a lot of both rightful kind of regulatory control of this data that all researchers and all individuals who want to use the data have to attend to. But at the same time, in order to make progress on some of these very hard problems, we have to be able to share this data. So finding a way that we can safely share this data is critical. Going back to the example that I gave you in cancer, any individual cancer might have an unusual, there's a long tail of mutations. They may have very rare mutations. And for us to learn about, that specific type of disease, we have to be able to share data among researchers to be able to do that. So how do we do that in a way that balances privacy with that, I think, is critically important. And there are computational methods now that kind of help us to create simulated data sets, et cetera, but we're still struggling with it in a lot of ways. The second way that I think that's really important in terms of the social aspect has to do with how we actually kind of use the data. I don't want to see necessarily a world where I go to the doctor and, I'm talking to a computer, I want to see a world where the best parts of kind of, humanity and our ability to interact with people, et cetera, are augmented by this data-driven kind of approach. So figuring out how to do that, how do we make the best decisions by combining the best of, human decision-making and computer decision-making, I think, is another kind of area in there.
So I think that's a great question. It's something like we talk about in my Introduction to Coding and Computational Social Science class for a couple weeks. I'm always amazed at how little students care about it, right, relative to how much I do, right? And I ask them why, right? And they often say, because I live in a world where it's out there anyway,
right.
Hugely. But I still believe there are deep privacy issues when you start particularly talking about the sort of mosaic theory of information in which you can learn about somebody putting different pieces of information together. So I have ways of making them uncomfortable by showing them what you can put together, right? Firstly about I do my life, right? About the digital information that's available, and that they could do the same thing, and that makes them more uncomfortable. And then they start talking about the privacy implications. This is one reason I think we need institutions right, that people have to trust us, like with this data and this access, that we're going to honor their privacy. And not just me, because they can't really know me or other researchers. They have to trust the institutions. I think this is a real place where universities need to be a leader. I think we've fallen slightly behind in the reputation game to corporations. I'm shocked at the trust that people have in corporations often with their data. I'm not shocked that they don't trust government with it, right? But there was maybe a little bit less, that we have less of a boost in trust for a university than I think we should, right? And I think we can get that back with some technical solutions and making people understand those about how we can use data, right, in a private way and share it for replicable research and other that doesn't give away people's identity, right, and other things that they'd be uncomfortable with. The second is about use, which you talked about, which I think is hugely important, that as we actually get better at doing things, like, so I was on a panel 2 weeks ago, like in Sweden, where we were talking about forecasting protest, right, and somebody brought up the case, like, man, if you were a dictator, wouldn't you love to be able to forecast protests? Right? Like, you shouldn't do this, right? Like, if you guys do this project and you do it well, right, you're helping repression. And, my answer to that is, are you really naive to think that they're not doing it already? And that, one of the important things is to have open source tools to level the playing field. I think one of the things that came from the Snowden revelations, and I study a lot of sort of information and national security secrecy because I'm really interested, right, in how information is used within government. And, these revolutions have not been lost on governments and how they use it. And one of the roles I think that we can play socially is by offering open source tools and other things that can level the playing field and empower groups, right, that don't necessarily have like a security apparatus that can go do these things. But that takes some work, and there's still some discussions that we need to have about those things.
You said that there was harm in information getting out. He said privacy is important, and then brought up Snowden. Went to a group to Russia, had some relatively smart people in it, and we were talking about what are you going to do to make sure your data doesn't get out there, and the answer is don't worry about it, it's out there. What harm do you see? I mean, what the four of you have talked about is sort of an open playing field, and I really wish it was not going to take 75 years because I'm not going to make it for the quantum computer. But what harm do you see in data being out there? I mean, I would be embarrassed that for someone to learn that I got a D in physics in the 8th grade because I pissed off the guy teaching the course, but who cares? I mean, what's out there about people that would be embarrassing enough that the data wouldn't be important, and it's out there anyway?
Well, I mean, I think, to be completely practical about it, I think it's the fact that, your particular name, your identity, is associated with some disease that you may have. I mean, and
So what?
Well, a lot of people feel that they don't want that information. I personally don't want that information
Why do 5
necessarily
people
for
with
out.
my name across just the United States?
Yeah. But it's not just your name. I mean, I think, talking about sort of the mosaic theory of information, I mean, you can determine a lot about individuals if that information becomes public, because you can piece things together. So you can know that, Rebecca Jacobson has this particular disease, or is being treated with this particular drug, or has this history of, domestic abuse, or
And
any of
suppose it
these
gets
things
to
that
him
people
with
don't
his
want
computer,
known.
And he's able to say, here's what you ought to do.
Yeah.
Or you go back to the electronic data records that you guys have been messing around with since like 2005, 2006, and someone actually solved Rebecca's problem.
That's the balance that I'm talking about. So just as an example, I worked in one of the very earliest biomedical data sharing projects. It happened to be in cancer. It was called the Cancer Biomedical Informatics Grid. And one of the neat things, it was a nationwide project. One of the very interesting things about this project was that it had patient advocates kind of embedded in every part of the project. And, it was interesting because I had come to the thing thinking, that patients would be very, very resistant to having this kind of information so openly available. But actually, those patient advocates, for them individually, the balance, boy, we could learn a lot. This might actually be something that creates a cure for me. Yeah, for them, the balance is quite different.
No,
so
but
I think it's
his
the
students have
individual.
told us where this is going.
Yeah.
Harm that you might have or I might see
Yeah.
isn't going to be there in 2 generations.
Because you think all of this data will be completely available.
You don't think it will? I can introduce you to 3 guys who can find out.
Yeah, I don't know. I don't know how publicly available to everyone on the planet will be. I'd be curious to hear do you think all medical information on every patient will be publicly available? I hope not.
I don't because of the worry, but most of it's about the mistrust of other people, right? So there's worry about insurance companies, right? And prejudices of things. So imagine that we get really, really good tools to measure IQ, and that becomes part of and it's accurate, right? And that becomes part of your file. Like, do you want that? Right? Like, I really wouldn't want my IQs compared to you guys. Like, I'm telling you. I want that private, right? I think that, like everyone else prior, is that it's more than maybe what it actually is. So I want that information private. I think that's one. I think one other thing that gets back to this is that we don't live in a perfectly transparent world. And the transition from, like, privacy, like, to more transparency that could have some good is really messy. It's really messy socially because it's about asymmetric information, right? It's about what you know. So, like, just think about, like, the recent election, right? Transparency on one side, right, has real costs relative to being able to keep secrecy. Whenever you're in a competitive environment, there are benefits to keeping secrets. And as we have asymmetries in information, there's going to be asymmetries in the ability to compete, right, and get benefits from that. So even if we agreed, and I'm not sure, like, I do think there are huge benefits to transparency, but maybe at the right times for things. But the transition to that world is going to be quite messy, potentially unequal, where you can have people paying, for their privacy and other people not with that choice. Those are things I think we have to think about.
I think we have a comment back here or a question.
And just an easy way to shoot down with the growth in AI, with the growth in AI and the scaling of computation and stuff, there's too much of your information out there and too much of your genetic information out there. If we start to be able to map it and really understand the computation associated with genomes and whatnot, with too much information, we can kind of almost create an AIU. And so, I don't know, like, and that's maybe kind of far out there, but at the same time, with the scale of computations and cores, and we get into quantum processing, we get, I mean, with literally all the information out there, we can basically create a snapshot of you. And that's kind of scary, and you can even predict maybe what passwords you would guess. It's just, I mean, the potential is awful.
Some people might say the potential is exciting. I think that's.
So it turns out that the Graduate School of Public Health has a simulation called FRED, 300 million agents in an agent-based simulation, which is a pretty good model of the US population. Now, it's not really quite at the point yet where those agents are models of you and me as individuals, and we don't know exactly what your preferences are in cars and things like that, but yeah, it's getting to the point where if somebody really wanted to, and there are all kinds of precedents for this. There are all kinds of technologies that are sort of moving in this direction. Someone really wanted to, you could build a very high fidelity simulation of pretty much everybody in the United States. Now, is that a good thing or a bad thing? And I think this is Rebecca's point, Michael's point also. It's both. Right? It's a good thing and it's a bad thing. What we know about the opioid epidemic here at Pitt, we know because of that simulation, FRED. Right? It's a good thing. It's also a bad thing. So let's look at it from a technological standpoint, and I want to talk about a program one of my favorite programs that was started at DARPA called Brandeis. It was called Brandeis because Justice Brandeis was the first person to talk about the right to privacy. The idea of the Brandeis program is that you should be able to say what happens with your data. You should be able to say, I want my medical data used by medical researchers. I don't want my financial data used by insurance companies. I want right? You get to dial how you want your data used. That's a magnificent happy medium that might change, might shift the balance to where data becomes a common good rather than a common good and a liability. Right now, it's both a common good and a liability. You can be badly hurt by having your data out there. If we could make it possible for you to specify how your data was used, then data then really would become a public good. And I want people to think about that idea, data as a public good. Think about data the same way you think about vaccinations. For you, it's actually not a good thing, right? You have a chance of dying. Your kid has a chance of dying, but you do it because it's a public good. You should be putting your data out there because it's a public good. Why? Because with that data, we can make the world a better place. And the reason I love the Brandeis program at DARPA is that it puts technological controls in place so that people can start to recognize that data is a public good.
What percentage of those people, when, you know, the screen comes up and it says, are you willing to have Apple or Dell or, you know, IBM have your data for your use? What percentage of us are saying, sure, go ahead, and what percentage are saying, no, I don't want you to know about my dumb mistakes?
I don't know.
Because that's, you know, the Brandeis principle and making it available, I mean, is a solution, but it's not going to work. If you told me your financial data were unavailable and I was making you a $200 million loan so that you could implement her program, I'd want to know a little more about you.
Is that an offer?
No, I'm just saying, if I were a bank, is that an offer? You think I can do it?
We got a question here and a question here.
Oh, for me, so I just like to respond to the idea about like privacy. So, like these companies like Facebook, Google, and like they have our information, like they have it, but it's not like Google or Gmail or like Google Maps can read our emails and like that people can access it because it's all encrypted. So they can still use that information to like create better algorithms and like help you out, but it's not like any employee or anybody there can access it or use it because it's all encrypted. And I want to say that I think that you need to protect privacy because first on the capitalist market, if you allow people's information like their like mental state and all that, and you can perfectly price discriminate. So like if you say, oh, this person, I know his history, he'll pay $1 million for this. Oh, this person will only pay $50, and then you can see that like that would happen. That would like be disastrous. And on a personal level, at least that's my opinion. I think perfect price discrimination would be disastrous. And on a personal level, like right now, everyone breaks like one kind of law, like a local, federal, state law, like every single day. So, and not even that, like your life can be just destroyed by like some random thing, like oh you did something that was once legal, like did marijuana, or you had an affair, or all these different things that if people can get their information on, then they can just character assassinate you, and then it can destroy your life just because your data is flowing out there. And you already see that with like politicians and like people with too much power, just like finding information on people. And so you need to protect some privacy because the laws are arbitrary and they change, and you need to have some kind of protection against a state that can just throw you in jail because it's politically convenient for them. So I think you need to protect privacy, which you just need to protect your privacy of your information. That's my opinion.
And yet,
So I sort of often thoughts of, you know, for the public good and also privacy. You know, I was thinking about how, you know, we have Fitbits, we all have smartphones, we all have, you know, devices that are always picking up data, you know, from either the microphone or, you know, this is telling me how many steps I've walked. You know, with going to the perfect good of like law enforcement, you know, what are some challenges or potential positive goods for, you know, solving crimes or, you know, sort of stopping crimes from happening?
Well, I'll tell you one that doesn't work. And I'm going to tell you this because I think we actually have to be very careful about how data mining is scrutinized. I mean, I think at the moment people are so excited by what you can do that they're not looking too carefully at the mistakes that algorithms are making. But we've seen mistakes in credit scoring, and we've seen mistakes in racial bias and things like that. But the one I read about the other day is a particularly nasty one. It's a company called Pre-Pol, and it predicts where crimes are going to take place. And lots of police departments are using it. And what happens is they run Pre-Pol, and Pre-Pol says, send your squad cars out to such and such a place because we think that there's going to be a higher than usual incidence of crime there. So they send their cars there, and of course the guys look around for someone to arrest, and they find someone. And Pre-Pol says, see, we predicted it. And it's beginning to look like it's just snake oil. Right? It's beginning to look like it's self-fulfilling prophecy. So that's not a strong answer to your question, could you do better with crime prevention? Almost certainly, yes. But what I am saying is be careful about data mining algorithms and what you believe.
Can I speak to that quickly too? So I agree with that wholeheartedly. So this is this growing push towards predictive policing, right? That's out there, and there's some pushback, right, about what it does and potential inequalities that result. But like, one of the things is like people just have to be like, everyone's got to be a better social scientist about this, right? Like we all have to be better at understanding that like this is a tool, right? And it could be useful. And there are people trying to sell you things, right? Because they make money off of it, and that's good or bad. But even more like fundamentally, right? We are actually really bad at like calculating probabilities and then updating like what rules work and don't work, right? And this is exactly like this idea that, oh, I found it, therefore this tool is great. Like you could have missed a bigger robbery, right? Somewhere else. And part of this is just, it gets back to the liberal arts point almost. Like we have to be able to, I think, technological challenges and tools are complicated and hard and exciting, and there's so much new things out there, and we have to raise our capacity, right, to be able to judge, value, and use them. And that's one of the things that I think we need to train and do and be, like as a community. And I think it sort of ties together almost everything like we've talked about. We need to be able to predict, right, and compute these things more accurately. We need to be able to like value and judge them and know how to use them. And we need to be able to train people, like to be able to harness them and improve them, right? The last point is the problem with predictive policing, in my view, is that it's not iterative. Like people take it as a solution and then they just act on it without seeing the mistakes, right? The thing that should come from like, how did we get these great tools? Is because like people sat around and iterated over and over again on tasks, making mistakes, critically looking at the mistakes to build better representations of the problem, and then doing it, right, as much as they can. And then other people coming by and say, you know what, your system sucks, right? We can do this better. And this competition across teams and across iterations. And we need to do that in our daily lives more. I mean, it's the real scientific method. It's not the like scientific method that fits on the foam board, right? That's just linear, and you start with a hypothesis, right? And it's right or wrong, and then you stop, right? It's how we learn from data and how we update and how we continue to do it.
Follow-up question. So as you guys were talking, I started thinking a little bit about how forensic science changed sort of, solving crimes. How maybe now technological, like, I don't know, science or whatever you call it, could help solve crimes. Like, what are those sort of pieces that could potentially be, the difference between someone, getting away with murder and someone going to jail for life? Like, how do the laws break down potentially where that could be?
Yeah.
Are they allowed to access that information? Is it legally, just like with forensics, are you legally allowed to obtain someone's DNA? Like, those different balances.
We need a criminologist in the room.
Yeah.
Computational criminologist.
I think those are the sort of interesting questions that can be addressed when we start bringing together social scientists with information scientists, with physicists who are all working in this area but can't individually answer those questions. And I think that's the excitement that we see around this whole area of data and information. And with that little wrap up, I'm going to thank our panelists and ask you to join me. And thank all of you for coming today. Those of you who are going to the football game, I'm just supposed to remind you, you can get a bus right over in front of the Cathedral of Learning. So thank you again, and thank you.
Actually, I want to start with you,